Up to this point, we've talked about electron regions, and what we've said about electron regions is that, let's just count the bond, a double bond, and a lone pair. Let's just count them as the same thing, call them just a region that the electrons are in, and then the shape that we're going to predict this ends up being is this trigonal, actually, hold on just a second. We're going to say, oh, this is like a trigonal planar shape, because that's what you get when you have a lone pair right here. That's kind of like up this way, and if we kind of think of like a line or something, that's kind of how it works, Well, the naming system with the electron geometry, it worked well enough for many molecules, but where it stopped working was this whole business about saying that electrons that are not in a bond, a lone pair, that can basically move all around in this space and do whatever they want, those electrons were not the same as electrons that are stuck in between two atoms and they can't do anything besides be between those two atoms. So what we found was that you can't think of that as like a line with those electrons in it. What you can think is that these electrons are kind of basically moving so fast that you can't really see them. And that's actually what happens is when we look at these instruments, what we see are not the bonds, but we actually see the atoms. So I can see this, this, and this. That's what I can see. I can't really see all the electrons, but I know electrons have to be there because I know that something has to be here, because otherwise, why would it look like it's in a bent shape? And so we found that there are subcategories, basically, and we call this molecular geometry. And anything that has a lone pair is going to have a little bit of a different molecular geometry. Now, if there's no lone pair, then it's the same name. But if there's a lone pair, the molecular geometry, it's kind of like you kind of squint your eyes, you make sure that the lone pair's in the right spot, and then you kind of pretend it's not there, and you see what the shape comes out to be. And like I said, this would be called bent. So we've got some videos coming up to using models to show you what they look like and to show you how the name changes with the different electron configurations. One more thing to note is that these guys also actually kind of push on this bond. If it were a pure trigonal planar bond, it would be 120. But what actually happens is that in their moving about, they actually smush those two things just a little closer, not a lot closer, so don't like overdo it, but they smush them together just a little closer. And instead of 120, it becomes 118. And the shorthand a lot of times we'll use to notate that, because everyone knows it's supposed to be 120, but the electron pairs are messing with it. Anytime there are electron pairs involved in a molecule, and we're using all these different names like bent and T-shaped and seesaw and all these funny names, we'll just say, well, the bond angle is going to be a little less than 120. And when you take organic chemistry, you'll find out all about these different angles and you'll have them memorized and everything. But we only need you to say something's less than 120.